So here's the first real question. If the universe has been expanding for 13.8 billion years, what's going to stop it? In 1998, two teams of scientists set out to solve what seemed like a simple problem. They wanted to know how fast the universe was slowing down. Not whether it was slowing, that part seemed obvious. Gravity pulls things together. The universe exploded outward 13.8 billion years ago. Of course, it was decelerating. The only question was by how much. Both teams spent years measuring distant exploding stars, supernovae, some of the brightest events in the universe. Each explosion follows a predictable pattern, which makes them useful as measuring tools. By studying how far away these explosions were and how fast they were moving, scientists could map the universe's expansion over time. But when the results came in, both teams got the same answer, and it was wrong. In a way no one had prepared for. The universe wasn't slowing down, it was speeding up. Something was pushing everything apart, faster and faster, with no obvious source, no known cause, and no place in any existing theory. Scientists called it dark energy. And that single discovery quietly cracked open one of the biggest questions in all of physics, a question that still doesn't have a final answer today. If the universe is expanding, could it ever stop? Could it reverse? Could it collapse and then explode again into something entirely new? In other words, could the Big Bang happen twice? To answer that, we first need to understand what the Big Bang actually was, because most people picture it wrong. It wasn't an explosion in space. There was no empty room that suddenly filled with fire and light. There was no center point where it all started. The Big Bang was the expansion of space itself, from a state so hot, so compressed, so unimaginably dense that our current understanding of physics simply breaks down trying to describe it. Think of it this way. Take everything you can see, every star, every planet, every galaxy, every atom of air in your lungs, and squeeze it smaller. Keep going, past the size of a city, past the size of a building, past the size of a marble. Keep going until everything that exists is packed into something tinier than a single grain of sand. That's roughly the scale we're talking about. And then, 13.8 billion years ago, it began to expand. Not into something, as something. Space itself stretched. Matter cooled, atoms formed, stars ignited, galaxies assembled, and the expansion never stopped. It's still happening right now in every direction, at every point in the universe, simultaneously. For most of the 20th century, physicists believed the answer was gravity, and the logic was clean. Gravity pulls things together. The more matter in the universe, the stronger the collective gravitational pull, trying to slow the expansion down. Given enough time and enough matter, gravity would eventually win. The expansion would decelerate, slow to a stop, and then reverse. Galaxies that had been drifting apart for billions of years would begin drifting back, slowly at first, then faster. The universe would start to shrink. Temperatures would rise as everything compressed. Radiation would intensify. Structures that took billions of years to form, galaxies, stars, solar systems, would be torn apart and pulled inward. And at the very end, everything, every atom, every photon, every piece of matter and energy that has ever existed would be crushed back into a single point. Scientists called this the Big Crunch, a perfect, violent mirror image of the Big Bang. It sounds final. It sounds like the end of everything. But here's where it gets interesting. What happens at that final point? When everything is compressed to infinite density, what comes next? This is where the standard equations stop working. In general relativity, the theory that describes gravity and the large-scale structure of the universe, extreme compression leads to what's called a singularity, a point of infinite density, infinite temperature, zero volume. And at a singularity, the math breaks. Time stops behaving like time. Space stops behaving like space. The theory essentially tells you, I can't describe what happens here. For decades, that was considered the end of the conversation. The universe collapses, the physics breaks down, story over. But a different group of physicists had a different idea. What if the equations break down not because nothing happens, but because we're using the wrong equations? General relativity is the best theory of gravity we have, but it doesn't account for quantum mechanics, the rules that govern the very smallest scales of reality. And when the universe is compressed to extreme density, quantum effects can't be ignored. They become the dominant force. A framework called loop quantum gravity attempts to bridge this gap. In this model, space is not smooth and continuous. It's made up of tiny, discrete units, the smallest possible chunks of space that can exist. You can't divide space infinitely. There's a fundamental limit, like pixels on a screen. And when the collapsing universe reaches that limit, when space has been compressed as far as it physically can be, quantum effects generate a repulsive force, a kind of pressure that pushes back against further compression. The result? Instead of collapsing into a singularity and ending, the universe bounces. This is called the Big Bounce, and it changes everything about how we think of the Big Bang. If the Big Bounce is real, then the explosion we call the Big Bang wasn't the beginning of everything. It was a transition point, the moment a previous universe, after billions of years of collapse, hit that quantum limit and rebounded into expansion. Our entire universe, every star, every galaxy, every moment in history, might be the aftermath of a universe that came before us. And if it happened once, the question follows naturally, will it happen again? That question depends entirely on one thing: dark energy. Remember the discovery from 1998. The universe isn't slowing down, it's accelerating. And the force driving that acceleration, dark energy, makes up roughly 68% of everything in the universe, more than all the matter and radiation combined. Here's the problem. We don't know what dark energy actually is. We can measure its effects, we can observe how it shapes the expansion of the universe, but its fundamental nature, where it comes from, what it's made of, whether it behaves the same way throughout time, remains completely unknown. It is one of the biggest unsolved problems in all of science, and that uncertainty matters enormously, because the future of the universe and the possibility of another Big Bang depends on what dark energy does next. If dark energy stays constant, the universe expands forever. Galaxies drift so far apart that they eventually vanish from each other's view. Stars burn out one by one. Black holes slowly evaporate over unimaginable timescales. The universe doesn't end with a bang or a crunch. It fades. Quietly, gradually, over trillions upon trillions of years, into a cold and empty state where nothing meaningful ever happens again. This is called the heat death of the universe. No collapse, no bounce, no second Big Bang. But if dark energy weakens over time, even slightly, gravity could regain dominance. The expansion slows, the universe pauses, and then it turns around. Everything we described earlier, the big crunch, the bounce, the new beginning, becomes possible again. And there's a third option, perhaps the most dramatic of all. If dark energy strengthens, if it keeps increasing, the expansion doesn't just continue, it accelerates so violently that it eventually overpowers every force in nature. Galaxies are torn apart, then solar systems, then planets, then individual atoms. The universe doesn't collapse and it doesn't fade, it tears itself to pieces. This scenario is called the Big Rip. 3 possible futures, 3 completely different endings, and the deciding factor is a force we don't yet understand. There's one more idea worth considering, one that takes the question even further. Some theories in modern physics suggest our universe isn't alone. In certain versions of string theory, our universe exists as a 3-dimensional surface called a brane, floating within higher dimensional space. Other branes exist nearby, parallel universes drifting through dimensions we can't see or detect. In this framework, the Big Bang wasn't caused by compression and rebound. It was caused by a collision, 2 branes drifting through higher dimensional space and crashing into each other. The energy from that impact created everything we know. And if 2 branes collided once, there's no physical reason they couldn't collide again. Another impact, another explosion, another universe born from the wreckage. In this picture, our universe isn't a single story with a beginning and an end. It's one event in a much larger, ongoing process.